Okay, so let me erase, and we'll be back to make that link. Okay, so this has been a relatively mathematical lecture so far, and it's now time to reap the payday. It's time for the big miracle of the day. Okay. We're gonna relate this abstract combinatorial quantity B and K to learning. Specifically, we're gonna link it to the growth function of a hypothesis set. Okay, and I mean this is just beautiful, and it's a very short link to make. But before I go and make that link, let me remind you, the last lecture we talked about growth functions and we computed it for some hypothesis sets. Okay, so we did the 2D perceptron, the 1D positive ray, and the 2D rectangle, the positive rectangle. Okay, this was the axis aligned positive rectangle. Okay, and then for various n, okay, so for n equals 1, 2, 3, 4, 5, and let's say 6. Okay, we computed m sub h of n. Okay. Now for the 2D perceptron, it was you can shatter 2 points, you can shatter 1 point, you can shatter 2 points, you can shatter 3 points. Okay, so 8 and 4 points. No set of 4 points can be shattered. So this was 14. The crucial thing is that it's less than 2 to the n. So let me put 2 to the n here. Nice lines. Okay, so 2 to the n is 2, 4, 8, 16, 32, and then 64. Okay, so that was the 2D perceptron, and then 5, it's going to be less than 32 because you can't implement all the dichotomies on 14. 6 is going to be less than 64 and so on, but we didn't compute those. Okay, for the 1D positive ray, we actually computed the growth function. It was equal to n plus 1. Okay, so n plus 1 is equal to 2 here, and here it's already 3. Okay, and so we have identified a deficiency of this infinite hypothesis set already at 2 data points. So the positive ray cannot shatter 2 data points. So there's some dichotomy it cannot implement, but and that's easy to figure out. So remember the positive ray. At some point, it's positive to the right. So if you have the dichotomy plus minus, it cannot implement it, because to implement the plus, you've got to put the threshold to the left of the plus, and then everything is going to be plus, including the minus, which means it cannot implement plus minus. Okay. So already at 2 data points, there's no set of 2 data points which can be shattered by the 1D positive ray. What that means is it's deficient. Already its deficiencies are sort of showing up at 2 data points. We say that n equals 2, n equals 2 is a break point, and n equals 4 is a break point. Remember we had this practice with break points. Okay, the 2D rectangle was more interesting. Okay, so here we actually computed this. It was 4, 5, 6. So this is an example where we could actually compute. Okay, and the 2D rectangle was 2, 4, 8, and things were looking good until we got to 5, where we didn't compute the growth function. We proved that it's less than 32. So less than 32. So I'll put it in red. Okay. Less than 32. In other words, it's broken. Okay, and that's interesting too. Okay, so all the uncountably infinite hypothesis sets that we try get broken at some value of n. In other words, there's no set of 4 points, there's no set of 2 points, there's no set of 5 points that those respective hypothesis sets can shatter. Okay, so they're deficient. We've identified that they're not as complex as one might have thought by just looking at how many hypotheses there are in there. Okay, so the growth function, let me remind you again the definition. The growth function, m sub h of n, for the hypothesis set n, is equal to the max number of dichotomies that can be implemented on n points And you get to pick those endpoints. You're trying to maximize the number of dichotomies. So let us suppose that, your hypothesis set, like all the ones we tried, has a breakpoint. So there's some value of n that breaks it. So let k be a breakpoint point for h. Okay, so what does that mean? No set of k points can be shadowed by h. Okay. And now let us consider m sub h of n. It's a list. It's the maximum number of dichotomies that the hypothesis set can implement on any set of n points. So let us suppose that that maximum number of dichotomies is realized for the set of points x1, x2, x3 up to xn. So on this set of points, if I go through all the hypotheses in H and list all those dichotomies, so I'm going to have a dichotomy here, plus, maybe plus, maybe I can implement all the plus, and then plus, minus, plus, and so on. I list all the dichotomies. I'm going to get m sub h of n dichotomy, because this is a set of points that realizes that maximum potential of h. Okay. And now remember, let's consider the case where n is greater than k. Okay. Or n is greater equal to k. So now let's consider any subset of size k. So consider any subset of size k. Subset of size k. And I ask, if we look at if we focus in on those k points and look at these dichotomies on those k points, I claim that those k points cannot be shadowed. Because if they were shadowed, then k would not be a breakpoint. So, any subset of k points is not shadowed by these m sub h of n dichotomies. Okay. And why is that? That is because k is a breakpoint. And so there's no set of k points that can be shadowed by the dichotomies in H. And these are the dichotomies in H on those k points. Okay, so it cannot be shadowed. Okay. So that means I've listed some dichotomies. Okay, they're all distinct, and for these dichotomies, no subset of size k is shadowed. But B of nk is the maximum list of dichotomies that are possible, period, on any n points, such that no subset of size k is shadowed. This may not be the maximum, because these are just the ones that came from H. Okay, so these are the special dichotomies that H implemented. Now, you might be able to add more dichotomies to this list without shattering any k points. It's just that those other dichotomies you can add are not implemented by H. But whatever H can implement, we know that, B and K is the maximum number of dichotomies you can list on n points, so that no subset of size k is shadowed. Okay? So what we know for sure is that this list cannot be larger than B and K. So m sub h of n is at most B and K. Voila! That is the link. This combinatorial quantity gives us an upper bound on the growth function for any hypothesis set that has a breakpoint k. So now let's state it as a theorem, full-fledged theorem. And it is worthy of a theorem. So we have proved the following theorem. Let H be any hypothesis set. Any hypothesis set. Okay. Then, one of two things is true. Either H is so complex, for example, H is every possible hypothesis on Earth, in which case it will be able to shatter any set of n data points for any n. Well, okay. As long as those data points are distinct. So if H is any hypothesis set, then one of two things happens. Either, okay, bullet point, H is so complex that it never gets broken. So no matter what n you give me, I can find a set of n data points with which H can shatter. Now, it turns out that you can get H's that have this property, even that are not as complex as every possible hypothesis set. And you can see some of the problems for some details. But, so H is so complex that it never gets broken. So you can find n data points which it can shatter for any n. In this case, m sub h of n is equal to 2 to the n for all n. Okay? That's the definition of H never gets broken. Its growth function is always 2 to the n. Remember, this growth function, if we succeed in putting it in the error bar, is of no use to us. Okay. Or, while H may be, let's say, infinite in size or uncountable or what have you, for example, like these hypothesis sets, so, or H does get broken. So that's the second case. H does get broken. In which case, H has a breakpoint. It has a breakpoint. Let's call it K. So for example, in this case, the 2D perceptron has a breakpoint 4. The 1D positive ray has a breakpoint 2. And the 2D rectangle has a breakpoint of 5. Okay. And if it has a breakpoint K, then we just proved, then m sub h of n is at most b of n and k, which is at most n to the k minus 1 plus 1. There's a typo here. This should be k minus 1. K minus 1. This should be k minus 1. K minus 1 in those bounds. Okay, so theorem. Okay, so this means that the breakpoint for H plays an important role in bounding m sub h of n for all n. So let's see what that bound looks like in each of our 3 cases here. So, bound. What does the bound look like? Okay. So, in this case, for the 2D perceptron, the breakpoint is 4, so k minus 1 is 3, so less equal to n cubed plus 1. The breakpoint is 2, so is k equals 2, so k minus 1 is 2. Sorry, k minus 1 is 1, so less equal to n plus 1, n to the 1 plus 1. And that, in this case, is achieved, because we computed it exactly as n plus 1. And in this case, the breakpoint is 5, so less equal to n to the 4 plus 1. Okay. Now I just want to pause and let this sink in.